Hello everyone. Today we're going to be going over the Educator problem, detect cycle in an undirected graph. As you can see, this one is marked hard, and I think conceptually it's not a particularly difficult challenge, but just because the graph is, first of all, undirected, which means we have two directions that any edge can go, and then furthermore, the fact that the graph can have disconnected vertices, it makes the implementation a little bit tricky. So the goal of this video is to kind of just like talk through the logic behind what we want to do and how to solve it. So let's just get right into it. So given an undirected graph, we want to write a method to detect whether there is a cycle in it. And that's all we have to do. So if we detect there's a cycle, we immediately, boom, return true. That's it, we're done. And then if there isn't a cycle, we return false, and then it'll handle it for us at the end. So the function is going to have the following signature. It'll give us any cycle and a graph object, and they've defined the graph and edge struct for us. So an edge is going to be two integers. It is going to have a source and a destination. And source is going to be source, dest is going to be dest. The graph is going to look like this. It's going to have a number of vertices, which we're going to query. That's going to be useful. It's going to have an adjacency list. In this case, it is going to be a vector of ints. Pretty easy. And then its constructor, you can pass it the vertices. You can make the adjacency list big enough to sustain all of those. And then for all of the edges, we will populate our adjacency list like so. So great. What does sample input look like? Well, we're going to say, okay, we have 8 edges coming in. And then in a list, we'll do each edge one by one. And note that it's all in ascending order. It is undirected, so of course there is an edge from 1 to 0 as well, but just for convenience, we're just going to do smaller number to bigger number, and we'll also reflect this when we write our code. And then what the internal workings of this code is going to do, it's going to handle for us. It's going to tell us if the graph contains a cycle, and if it does, that means there is a cycle. So let's just run through this graph example we have right here. Okay, so let's see. We have 0 and 1. Oh, it's kind of highlighted. Okay, we have 0 and 1. So let's make our edge here. Of course, it's undirected, so it goes both ways. I'm just not going to draw the arrows. We have 0 and 2. Okay, cool. Edge between these guys. And then 1 and 2, and we already have our cycle, right? And of course, there's more edges we could have, but at this point, we know we have a cycle. But, let's draw out the rest of the graph just to see. Okay, so 2 connects to 6. Cool. 1 connects to 3. Cool. 3 connects to 4. 3 connects to 5 as well. And 4 connects to 7. So you can see in this case, we only have the one cycle right here. Now, how do we detect this? Obviously, it's really easy to do when you're just looking at it, because you'll see that one node, there's a path that goes from one node, and then it ends up at that node. And of course, that's the definition of a cycle in general. If you can start at one node, go to some different nodes, and then end up back at the original node, then you have a cycle. But to really solve this question, we're going to need to think a little more deeply about what a cycle represents, right? Because right off the bat, probably the first thing you're thinking is, oh, okay, well then, if I need to detect if there's a cycle, let's just do a DFS of the graph for every possible node. And if our DFS ever lands on a node that we've already seen, say for instance like this, we're going to DFS to 2, we're going to DFS to 4, we backtrack, we DFS to 3, we go to 1. If from any node our DFS ends up on a node on that same node eventually, then we know there's a cycle. And this is a valid implementation that works, but remember we have a undirected graph, right? So we're also going to need to account for, let's say we have 1, 2, 3, 4, 5. If we have something like this, right? If we just look at the 4 and 5, we're not going to detect that there's a cycle between 1, 2, and 3. So we need to make sure that we're checking every possible node in the graph because there could be discontinuities. But a slightly or a clever property of cycles that we can use is actually, let's think about what constitutes when a graph has a cycle and when it doesn't. Okay, so let's say we just have 3 edges floating out in space, right? And now if we add one edge, there's no cycle. If we add a second edge, still no cycle. If we add a third edge, we now see that there's a cycle. And so what just happened? Let's add a 4th node right here, right? So we still have a cycle. But now let's remove this edge, and then we have this. We're down to 3 edges, and we don't have a cycle again. But now if we add a 4th edge, we're up to the number of edges being equal to the number of nodes, we have a cycle. And if we get a 5th edge, now there's 2 cycles. But of course, if there's 2 cycles, that means we have at least 1 cycle. So what's the pattern here? The pattern is that you're only going to have a cycle if your number of edges meets or exceeds your number of nodes, right? So let's see what that looks like. Because again, right now we have 1, 2, or in a connected graph, in a fully connected graph. So you can see right here, that doesn't necessarily make sense for this because what's this? We have 1, 2, 3 edges, 1, 2, 3, 1, 2, 3, 4 edges, and 1, 2, 3, 4, 5 nodes. So just looking at it, you're not going to think necessarily, like just using that heuristic, it's not going to tell you right away that there is a cycle. But what we can do is consider each little chunk of nodes separately. We can think of it as a separate graph. And so that's going to be the algorithm we're going to follow for this. So we're going to start from a node. We are going to DFS to find all of the edges possible between all of the nodes. And if we end up seeing that for each given like island in our graph, if the number of edges meets or exceeds the number of nodes, then we have a cycle. If we detect 1 cycle, we detect all of them, and we'll just do that for every single node in every single island. Now, one last little tidbit that you don't really need to comprehend for this, but it's kind of helpful. You can think if an undirected graph is fully connected and it has exactly n-1 nodes, that's just a tree, right? And we know a lot about trees. We've beaten them to death. We've done the AVL. We've learned about red-black trees, slate trees. And so you can kind of think of it in the sense like, okay, is it a valid tree is almost another way to think about if there's a cycle, right? Because if 3 connects to 4, this isn't a tree anymore. But as long as there's n-1 edges for n nodes, then we are not going to have a cycle. And if it's disconnected, but there's still no cycles, it's what we're going to call a forest. And that's a little like higher level graph theory. We don't really talk about forests that much in this class, but that's just a little bit of extra vocab. So that being said, let's get into writing the code for our edge detection. So now for the sake of convenience, I have my editor pulled up just because I'm a little more comfortable in it. It'll give us any like red squiggly underlines. Of course, recommended workflow if you're working on these yourself. Might be nice to just like throw up a VS Code window and work in there. But that's neither here nor there. You can of course use Educator. So let's get started. You can see up here, I've just kind of taken the provided, let me pull this up. I've pulled up the provided code just so it's there and it's gonna like do proper syntax highlighting and completion. With that being said, let's just get started into it. Okay, so what was the algorithm we talked about before? Well, we are going to want to do a DFS on every possible node and to get the edge list. Now, we're going to consider islands individually. If for any given island, there are more edges, or they're equal, or more edges than nodes, we've detected a cycle. And then if we detect 1 cycle, we can just return true, there's a cycle. Otherwise, if we go through all of our islands and we don't detect any cycles, then we can say false. All right, so let's start thinking about the code that we want to write. So of course, we're going to want to write a DFS function, and we're also going to want a helper to find a individual cycle. So let's just start writing out the outer code, and then we'll write the inner functions as we need them. Okay, so first of all, we are going to want to keep track of our, oh, that's weird. Sorry, the indentation is a little off. First, we're going to want to keep track of our visited nodes. So we can just create a set right here. Let's call it visited. And so this is going to be the numbers of the nodes we visit. And remember, that's okay because it's all just going to be index nodes. So that's cool. So we have that for all the nodes we visited. And now we can just go through all of the vertices in the graph. Because remember, our graph provides us num vertices. So let's do a little loop to go through that. So let's see. Let us say for I, int I equals 0, I less than graph.num vertices. Let's go through all the vertices. Okay, so first of all, because we're keeping track of visited, we want to make sure we're not just going in infinite loops in our algorithm, and we want to make sure that we are only going to be, we want to make sure that we're only going to be visiting new nodes, right? Nodes we haven't seen. We don't want to go through nodes we've already seen. So since we're using a set, we can use the standard way to tell if something's seen in a set. So we're going to say if visited.find I. So this is going to return either the, I think an iterator or the index of the thing in the set. And if that iterator ends up being the end of that node set, we know, okay, that, oh, sorry, not node set. If it ends up being the end of visited, then we know that item was not found in the set. So that's super easy. So, okay, let's say we don't know, or so the node we have hasn't been inserted yet. What do we do now? Well, let's, starting from that node, check if there's a cycle. How are we going to do that? Let's define a little function. Okay. So while we're here, let's figure out, or let's write our single cycle detecting function, right? So given a node, given in the graph, are there any cycles from that node? So let's just define it up here. Let's call it probably is cycle present. It's not the clearest thing, but we could say maybe is cycle present in island. Just something to show that we're starting from the individual items. Because remember, the graph could be disconnected, so we need to account for this stuff and this stuff separately. Excuse my poor mouse hand drawing. Okay. So let's see. Yeah, let's just call it is cycle present, and of course we're going to return a Boolean because the result of that is going to inform whether we have a cycle that we can return from here. So if there's a cycle present, and what do we need to provide it? We need to provide it the graph. Let's do a constant reference just for good practices. We don't really want to be changing our graph at all. And let's see what else. We need the actual vertex number. So let's just call it, we'll call it source. And then we need our set of nodes that we've seen so far, because we're going to continue populating it as we check for cycles. So again, we're not going to be doing an infinite loop. So in this case, we want it to be a reference to a set of integers. And let's call it visited like the other one, just to keep stuff consistent. Okay, great. So that's our signature. And now we can define our function. And just for the sake of it, we're going to assume that this is going to tell us return true if cycle is present for, let's say, sub or for island in graph. And I didn't close the parentheses correctly, but whatever, that's okay. So just using our function signature right here, it's going to return true if there is a cycle and false if there isn't. So we can just say, okay, if is cycle present, if there's a cycle, given our graph, the current node we're looking at, which is I, and the set of visited nodes, so we'll just pass in visited. If that ends up evaluating to be true, then we are going to return true. And so that way it's going to catch immediately if we find one cycle, there's a cycle, we can stop what we're doing. And then only if we finish this entire for loop can we return false. No, there's no cycles. We made it through everything. We checked everything and we found that there was no cycles. Great. Okay, so now let's go back and implement our is cycle present function. Okay, so what are we going to do in here? Well, like we said in our drawing, we're trying to figure out if the number of edges is less than or equal, if the number of edges is less than the number of nodes. If it's not less than the number of nodes, if it's equal to or greater, then we know we have a cycle for the given island. And the given island part is really important because we as we saw in our other example, it's possible overall to have less edges than nodes but still have a cycle if the little islands are disconnected. So how are we going to keep track of each island? Well, given that any node we visit here is not going to be it's not going to have been visited before, right? Because if we if we went through an island already, those nodes would have already ended up in visited. So we can assume that for each one of these, we're looking, each time isCyclePresent gets called, we're looking at a new island. So we can define an edge set for each island individually. So let's create our edge set first. So let's say set, I believe in the graph, the edge is technically its own struct, but we can just use a pair and then use its constructor. It should be easy. So let's say our set is of pairs of integers, or sorry, pair of integer and integer. And from there, let's call it visited. No, it's not necessarily visited. Let's just say edge set, because these are the edges that we've seen so far. Cool. Okay. And then we also want to keep track of the initial size of the nodes that we visited and then the ending size, right? Because we're passing in our existing visited set. So it might already have some nodes in it, and we don't want that to, I guess, influence what our calculations. We're only concerned about the individual islands. So what we can do is just keep track of the initial size of our node set, and then we can see how much it grew later, because the amount that it ends up growing is the amount of edges, or is the amount of nodes that we've found in our little island. So let's just call it size init, sure. And let us say that is equal to let's say it's equal to visited dot size. And so once visited grows, we can compare against the size and see how many nodes are actually in this little like island that we're looking at in our graph. Okay, so now we need to actually populate the edge set with our edges, and we need to visit more nodes. So what are we going to do about that? Well, now's the time to implement our DFS function. So let's go up here, and we'll call it here, but let's take a pause. We'll say, I don't know, to do implement DFS. So let's populate that edge list using a lovely little DFS. So let's make our DFS function. Yeah, okay. So it doesn't really need to return anything since it's just populating the list we're going to give it. It's just populating the list that we're going to give to it. We'll call it DFS. And so what does it need? It needs the current node that we're starting from. It needs the graph that we're working with. So we can do same thing, constant reference, good practice. We don't want to, excuse me. Sorry, I had to sneeze there. We don't want to, copy the whole graph in memory, and we don't want to change it. So constant reference. And then we want our edge set that we defined here. So we'll just define it with the same parameters, a set of pairs of ints. We will call it an edge set as well. And we aren't making it constant because we do want to modify it. And then finally, we need our set of overall nodes that we visited so far. So we'll call it visited. Cool. So what are we going to put in here? Well, obviously, first thing we need to do, we're looking at this node. We need to visit the current node so we don't go into an infinite loop. So put node in visited. Let's do that. Let's say visited. Sorry. Can I spell? Visited.insert current node. Great. So that's in. And now that's kind of our starting point. So now we need to go through every single neighbor of our current node. And luckily, our graph provides to us an adjacency list implementation. And so that's super easy. We don't have to like query the matrix or anything. We can just go through all of the edges. We can go through all of the edges in the adjacency list and figure out what's in there. So let's go through our adjacency list right now. We can just do a little for loop. We want a, okay, it doesn't have the auto completion for, oh, it does. Okay, cool. So for every neighbor, that is not C++ syntax. Okay, I think it gave me a strange, like a Python completion or something. We don't care about that. Okay, so for all of our neighbors in our graph's adjacency list for our current node, so we'll say current node. So basically, for all the neighbors of the current node that we're getting from the graph that we've been provided, let's figure out, or let's populate our edge list and our node list. Okay, so how do we want to do this? Well, ideally, we are just going to insert the new edge that we get from the current node and its neighbor into the list. So that'd be something like we want to edge set dot insert. Sorry, insert, we would just insert the cur node and neighbor. However, this is an undirected graph, so if we have, for instance, if we have a node from like 1 to 2, if we have a node from 1 to 2, that means we definitely also have an edge from 2 to 1. And sure, we could include these separately, but I feel like that's kind of redundant. So what we can do is just a little bit of housekeeping, and we can make sure that, let's just arbitrarily say we want these edges to always be sorted, right? So we'll just say, we'll do the smaller number first, then the bigger number for any edge, and then that'll kind of make it easier to think of what we're doing. So instead of just inserting the cur node and its neighbor like outright into the edge set, we can do a little bit of housekeeping. So a pretty easy way to do this, I mean, there might be a slightly more efficient way, but that's not really the main point of this problem. Let's just make a vector of the nodes we care about. So we can say vector of, excuse me, vector of int, we'll call it nodes. Let's call it nodes temp because we're not really going to use this. And let's say it is equal to, I don't know why it's doing weird stuff in the indentation, but whatever, not a problem. So we can say our nodes temp is going to be equal to the current node and its neighbor. And now, a really easy way to sort this, we can just use the STL. This would be standard sort, but I'm using namespace standard up at the top, so just for convenience, I'm just going to call it sort. So let's say sort. And the syntax for this is just the vector.begin, nodes temp.end, and this will sort the vector in place. Easy. And so now we can, instead of inserting the nodes just by themselves, we can take our sorted stuff from the list. So let's see. Also, I made a mistake here because this should be getting a pair. And otherwise, this would be inserting... actually, this should work, I think. I'm going to put a pin in this. This should probably work. So instead of getting just the current node and neighbor by itself, we can now just get the items from the vector. So if I change in here, we can, let's say we're doing a list in place. I don't know why it untabs every time I put a curly brackets, but whatever. And so we can say nodes temp, and it's 0th item, and then nodes temp first item. And so that should insert the pair quite handily into our edge set. And now we know for sure that it's going to be sorted. So that's easy. Great. And so we have our edge for each neighbor that we found, or we create an edge for each neighbor of the current node. And once we're done getting all of those nodes, here, let me format the code real quick. Once we're done getting all of those nodes, we can now move on to the next node to explore. So we've inserted the edge set. And now let's say if we haven't visited any of these neighbors, we want to then recursively DFS on it again. So same idea as before, where we were checking if the cycle is, same idea before where we're checking if it was visited. We'll say if the neighbor in our if we can't find the neighbor in our visited, meaning we haven't visited the node yet. Sorry, let me just type instead of speaking. Kid.end. So if we look, we don't find it. We know we haven't visited yet. Let's just go ahead and visit that node by recursing. So what are we going to do? Again, we have our base case. If it's already been visited, we're not going to recurse anymore. So let's just go in. We'll call DFS again. Instead of calling it on the current node, we're going to call it on the neighbor we're looking at currently. We will pass it the graph as usual. We will give it the edge set we're working with, and we'll give it our visited set as well. And so that's our DFS. Quite straightforward, just a standard DFS. Okay, so now it's the final step. We just need to apply our DFS to find out if there's a cycle. So let's come back to our isCyclePresent function right here, and let's see what we can do with this. Okay, so now we have our DFS, right? Let's just run this on everything, right? Or let's run it on this island, because the DFS is only going to find nodes within a given island, because, you know, the DFS is traversing over nodes, right? So if we start at 5, we go to 3, once we're done DFSing, we'll have seen everything here, but it would have no way to jump over to this island. So once we're done with our DFS, we're going to get all of the edges in the current island that we're looking at. So let's just run our DFS on everything. It'll populate the lists that we're going to give it. So let's run it on the source node we're checking for cycles from. Let us give it our graph. Let's give it the set of edges that we're working with, and this is for our particular island. And then, of course, let's give it our overall visited node set for everything. So great. This DFS is going to run. It's going to recurse and everything, and it's going to populate our edge list and our visited for the nodes in our current island. Okay, so now our initial size is going to come into play. So once we're done DFSing, our visited set is going to have grown by some amount. So the amount that it's grown is going to be the number of nodes in our current island. So let's just calculate that. So let's say int nodes in island, excuse me, not isnald, nodes in island is visited.size, because this is the current size after everything being added, minus size in it. So this will tell us how many nodes are in our current island. Okay, handy. Now, we're right there. So now we can go back to that thing we were checking earlier. So if there's greater than or equal to, if num edges is greater than or equal to num nodes, we know we have a cycle for that particular island, right? And this is going to be a little easier too, because that means we don't have to start at every node, DFS, and see if we end up at the same place. We can just get all of the edges in one round, and then check the edge numbers versus the number of nodes. So now, really simple check. We can just say, okay, if our edge set size, if that is greater than or equal to the nodes in island that we just calculated, then we are going to return true. We found a cycle. And then if not, we're going to say else return false. Cool. So let me format that real quick so it looks a little nicer. Great. And so with all that being said, that's it. This code should work if we paste an edge gator. So it'll run on each island. If there's a cycle, it'll return true. And then if we get through all the islands and we don't find any cycles, then we can return false. So I'm just going to copy all of this code from, I guess, here down. We're going to paste it into Edugator, and we're going to see, and we're going to hope this works. It should. Okay, let's run our code. Does it run? Set has not been declared. Okay. I'm going to include setup here. I thought it was including namespace standard to begin with. Okay, I'm going to throw in this this fancy little include right here. Bit standard C++.h just has everything in the standard library. I guess it's not included by default. So let me just hit enter a couple times. We're going to have all of our headers. Let's see if it runs now. Okay, graph contains a cycle. What was our test? This. That's what we expected to see. Let's just submit our code. As you can see, all of our tests passed. So just for a little bit of a recap, we use the fact that for any given, I guess, island in a graph, there's not going to be a cycle if the number of edges is less than the number of nodes. And then we just make sure to check each island individually. And if we get through all the islands and we find that there were no cycles detected, then we know there were no cycles overall. I hope this was helpful. Good luck in completing your programming quiz for this week or getting your extra credit, and I hope you have a nice day.